Hello, my name is Martin Šavc. I'm from the University of Maribor. I work with Professor Holobar, and my colleague here, Miloš.
I'm Miloš Kalc from the Science and Research Center Koper, and I have a background in sports science, so I'll be a little more practical, and Martin will be a little more technical. So we present some new tools, and this presentation will be maybe more a hands-on, maybe different than the previous presentations, and will not be that much into neurophysiology, maybe. So maybe a lighter topic, but still an important one. As I said, I'm a background in sports science. Especially in the last 4 years, I'm fully specializing into neuromuscular physiology, so doing a lot of EMG, H-reflexes, and high-density electromyography. I'm collaborating with Aleš, but in our group, we were a relatively small group of people, but in the Science and Research Center Koper, and covering quite some different topics. So sometimes we have some project that needs a lot of field measurements, so all of us have to contribute somehow. And one of those projects was a project that was financed by the Slovenian Research Agency and was about finding a new quality markers for the sarcopenic adults, so older adults. So in this project, we measured in the last year and a half, we measured almost 700 participants, so 700 older adults. And of course, we couldn't measure them using high-density electromyography or really fancy equipment. So the majority of the measurements were functional testings, like the fitness test, so sit-to-stand tests, or repeated sit-to-stand test, or the TUC, so the EUG time up and go test. So quite simple tests, but still a lot of work. So if you imagine what can we gather from this kind of tests, usually we can all count the number of repetitions in a given amount of time, or count the time for the task, so completing the task. So they're really low, basically informations. And of course, if someone took a lot of time to do a sit-to-stand test, it might be because of a neurophysiological decline, but also could be because some pain in the knee or some pain somewhere else. So we cannot differentiate what's actually going on. So it will be. I forgot to mention, this project is led by our PhD student Katarina Pusch. And but sometimes we want to have this information. So we want to have maybe more information about the movement. So, and one of the possibilities traditionally was, of course, to use motion capture technologies. Of course, here it's a fully 3D marker, 3D motion capture system. We can see. I bet that the majority of you probably coming from these sciences probably know already about these systems. There is, of course, a trade-off using these technologies. It's time-consuming. The equipment itself is super expensive, and also the analysis itself, it can be again really hard. Although these examples are in a really big labs, usually we are constrained in smaller laboratories. So bringing a lot of people in, it's quite challenging. There are maybe a different solution, might be the use of IMU based suits. So there is this lady, this gymnast, wearing a vest with many IMUs, so accelerometers and goniometers, and after the measurements, we can get a 3D model out of it. But again, it's suitable maybe for more field tests, so using in the field, but still it's not suitable for the use in elderly person, for example. Okay, doesn't work. Perfect. Yeah. So there are other solutions that are, of course, less precise. You have a few phone-based solutions that use all the accelerometer within the telephone or in the mobile phone or the pictures, so the cameras to, for example, calculate the power during the sit-to-stand test. And or more professional one, for example, this is an application of the IMU, a single IMU, usually placed on maybe the belly or the spine to measure the movement of the participants, which is of course easier to use. But with the development of the technology and especially artificial intelligence, we can see that there is new tools, video-based tools. So there are some activity. One of those tools is the so-called OpenCap, which was developed by Scott Delp and his group in Stanford, which has really long time working on biomechanics and biomechanical data. And basically, this tool allows you. Basically. Hopefully it will work. Yes, it works. Basically allows you to measure and to get a full functional 3D model of the body with only using two cell phones or two iPads, as we had here. And this is a simple measurement that we performed a few days ago just to have a demo. And after that, I will just Control W. Control W, okay.
That's what we want, right?
Yes. And yeah, so if you get again, we could have again a sit-to-stand test or repeated sit-to-stand test, and we could measure it with these cameras on the field, in the field, and get this model in basically minutes. Maybe you will see then the technical part that maybe will take a little long, but nevertheless, it's a faster recording and analysis than with marker-based systems. Yeah. And before continuing, we will do a short demo just to get a simple capture of the data, and then at the end of the presentation we will demonstrate the data. Hopefully, the system will work. If is someone from, I have to do this.
No, we can pick someone, but we have to start with the setup, right? So let's take a look at what simple measurement would look like. The iPads, the measuring devices we already set up. This is fairly simple, right? You just, if you have a tripod, it's great. You set up the cameras and make sure that you have a good view of the scene, more about how to set up the cameras, how to view the scene later. But right now, we have this web interface. So it's a web service where we can connect the devices and do the measurement. First, we do a new session. So the way it works is when we just need to get this QR code, when we start a new session, we get this code and get instructions which tell us to basically scan the code with the app on the devices. There is an iPhone app that we install, and then we scan this code, and this connects the device with our session at the moment. So it's fairly easy. They suggest that you take the iPad, scan it, and then set it up. I like to just do it this way, where I take a picture of the QR code, or if I have a laptop I can move, I just move the laptop in front of the cameras. But this works well as well. I have the picture, and then I'll just present it to each device to start a new session. And the application tells me when they're connected. Okay. So it's fairly simple, fairly quick. If you have two cameras, if you have three, you can have I'll say as many as you like, but at some point it probably stops working. The network isn't fast enough, but this is all we need. This part, then we click next, and we get to the calibration phase. So the calibration is done using a checkerboard pattern, got instructions here, you print it out, and we set it up so that all the cameras can see it at once. All this step does is it calibrates the cameras so that the system knows their relative positions to each other, right? So this is the more difficult calibration. If anybody is familiar with computer vision and camera calibration, usually the calibrations can be quite intensive, but here all we're interested in is the relative position, so it's fairly simple. We just need one picture of this calibration target in each of the cameras. In the web interface, we click calibrate, it takes the images, sends them to the server, and now it's processing them. It tries to detect the mask. Everything's fine. So we get a green. If it didn't work, we'd get a red, and it would be telling us one of the cameras couldn't see the checkerboard. So the next step is to take a neutral pose. So in order to make sure everything works correctly, the system wants us to take a neutral pose. There's an image of what kind of pose we should be capturing, something like this, before we start with the regular recordings. And any volunteers, anybody want to try this? You can also try it later. Maybe you do it first.
No.
Oh, great. So we do have to make sure that the person that is doing the neutral pose is standing in the scene. So the best, perfect. The checkerboard doesn't actually bother it, but it's easier if it's not there. We have to fill in some sessions. So they have like this online formula where you have to fill in who the person is, what their, if they have any issues, what kind of measurements we're taking. And I'll just use Miloš's account here.
Work with the height?
Yeah, it doesn't matter.
Okay.
It might use it for calibration, but in the end, it's fine. So we're gonna have a session name. We'll say HybridNeuro. This is summer school. And okay, we do need to accept that we're uploading the data and sharing and potentially sharing it, but we do get an option of how to share the data. This is mostly relative to the personal data that we fill out in their profile, right? The video, if we share it, still gets shared. So we click record. It's going to take the image. Once it's done, it's going to take that our subject can relax. So we're practically done. You can sit down or you can sit there. Now, at this point, the system needs to, it took 2 photos. It needs to process those photos. It needs to actually detect the person and try to do the 3D estimation of the model. So at this point, it might take a while. The way it works is any videos you take, they get sent on their server, and the server is the one that does the processing. This was fairly quick, so we're already on our way. But sometimes it could take longer, because if a lot of people are using the system, then you basically have to wait for other people to finish before yours can get processed, right? This is the first part, so now we want to do some recordings. Will you suggest some kind of exercise, or?
You can know whatever you want, but maybe stay within few steps. So
yeah. So it's important to keep the person in view of all cameras. So the way we set it up before, you can go up to around here, you can go back further, you can do almost anything. Try not to hide. We'll just do test or rec 1, do a recording. We're starting the recording, the camera starts capturing. Now you can, for example, you can take a few steps forward, turn around, take a few steps back and sit down.
Great.
It is, I wouldn't say that it's useful if the recordings are short, because the only issue is if the recording is very long, then the upload takes a long time, and then the processing will also take a long time, and usually you want to be fairly quick about it. Now, okay.
You can take a seat.
At this point, we're going to have to wait a few minutes, so we'll probably continue with the rest of the presentation. At this point, we have to wait for this to get processed. And depending on how many people are using it, again, this step might take a while. You can take multiple recordings, you can record multiple things, but then we have to wait here for this recording to get a green light, and this will tell us that it's finished, that we can check our 3D model estimation and reconstruction. But since we have to wait, we might as well look at a few other things. So these parts this technical part we already took a look at, right? The calibration, we need to put this target in the scene, and we need to take a photo of it from multiple cameras. And it's important that all the cameras see it at once. This is kind of a sketch that I draw of this. These little gray triangles, these are the cameras. The light green areas, that's the viewpoint, the area of the scene that an individual camera sees. And then the part where all the cameras see it, that's a bit darker gray. Should be fairly easy to understand. Here, the issue is that this camera was put behind the calibration target, right? So it can't see it. So, for example, this wouldn't work. This will be fairly important later. Then we have to take the neutral photos. We already see how this looks. We can also inspect it here. These are the images that we took of the neutral pose, and this is the 3D reconstruction in this interface that we can inspect. We can turn around and look at details if we want to. Now, for recordings, there are some developer recommendations and guidelines that they give you in order to get good recordings. So they suggest that you're using tight clothing with high contrast. This is tight clothing is good because then it's easier to estimate the positions of the markers on the body, right? Loose clothing could be bad. If you have very loose pants, the knees might not be as obvious where they're located. The high contrast basically means that if you're wearing like bright clothes like me, it's great because then they contrast with background, they contrast with each other. This is something that you also might want to take a look at, something you might keep in mind, but might not be very important. They suggest that at least one fast movement happens in each recording. This might be an issue, but we'll see that basically the service needs to synchronize our videos, right? We capture videos from multiple cameras, so we need to make sure that we know which frames match together, and it does this basically just through analysis. The 3D and 3D detection and reconstruction also gives it the information that helps it to synchronize the videos. But if the movement is very slow, if the person just stands there and just moves their hands very slowly, there might not be any good information for which to align the videos. So yeah, they suggest like quickly raising their hands at the start or something similar. Using a well-lit environment, this is pretty standard for any computer vision or any camera capture, right? Then avoid occlusions. So we'll see later on that when one camera can't see a body part, or when none of the cameras can see a body part, this causes errors in our prediction, in our 3D reconstruction and estimation. So again, this is something we might keep in mind when we're setting up the cameras. Avoiding background people and staying within the scene. And then the last one, keeping cameras at 40% degree angle. This means that the angle between our subject and the cameras should be around 30 to 40% if they are two, and they'd be front facing. Some of these I agree more or less with. We'll see through the examples that we'll be looking at, but all of them are important to get the best quality estimation. But sometimes you don't have the option, like you can't control how people wear. You might have to take these recordings in an environment that you don't control. But for modern computer vision systems, such as this one, this might not be a big issue. The errors aren't going to be extreme or might not be important at all. So here I had a few examples of these recordings, just normal ones. The first one was using 3 cameras. This was using just 3 iPhones that I borrowed from my colleagues. So this is an example of a good recording that we did, right? We tried to follow most of those recommendations. we have a simple background, nothing noisy, no, just our test subject is in the scene. We have 3 cameras, which should produce better results. And we get this kind of reconstruction. After we get the reconstruction, we also get some additional data. So we can inspect this 3D model, right? If there's something we're already interested in, we can zoom in, we can pan it around, and we can select fairly easily the specific moment we're interested in. So we just drag this timeline below, right? Or rotate the scene with the mouse. Additional tools that we have available is we can draw some simple charts. So I'm not sure which ones are useful. I might select one, but basically we have angles between limbs or around joints, hip flexion. We can select there, we can fill out the chart, we can give it a title. So you can get some kind of simple chart. I would say this is useful for a quick report. I'm not sure how many of you are. I'm not very impressed with the tool, but it's fine to get a quick graph of something you're interested in. Of course, or rather, I should say, additionally, shouldn't go back to session list. Okay, this is fine. No. Additionally, you can export this data. You can get, I think it just says so because I clicked back. You can export this data, you can get it. The data that you export is prepared to be imported in OpenSim. How many of you already know these tools like OpenSim? Okay, a few then. Fairly many. Yeah, so they are sort of developed together, right? And yeah, you export this data, you can export it in OpenSim, use these kinematics to then simulate or predict forces. But you can also get these if you're only interested in like these simple measurements that this tool makes, you can extract those as well. And later we'll see how we could synchronize this with other measurements we take, for example, EMG. So this is 2 cameras. The graph I exported, this was just knee angles from this video. It's fine. It's fine if you just want to look at it. I wouldn't put this in a paper. I would prefer to have a bit more control over how the graph is constructed, how large the text is. An example for 2 cameras, this might not be that important to just watch, because again, with 2 cameras, we can still get fairly good results. We don't need 3 cameras. 3 cameras might be more accurate, and in some cases, they do help. But here, 2 cameras still works fine. Do this? Oh, I can. Some standard issues that come up with computer vision software, right? Lighting and scene complexity. Usually it's a problem. We do want good lighting. We want the scene to be simple, especially when we have some kind of software that we have to wait for the results. We don't want to take the measurement and then wait for half an hour. We send the person home, and then we find out that the measurements were useless, that we didn't detect reconstructing. However, using modern machine learning, which this tool basically uses, the detection even in fairly complex lighting. Here, what we did was we took the opposite side of the room. Maybe we could check out the video. We took the opposite side of the room, opened the window, let the line shine in from the back of our subject, my colleague Leon, and still worked fine. Not perfect, there were some issues. But if these were the environmental conditions that I'm limited to, I'd say this still works fine. Interestingly here, we had more issues actually calibrating the system than taking the recording. The calibration target simply wasn't light enough to detect it. So we had to first put down the shades, turn on the lights, and then we could calibrate it. Then if we put the shades back up, the calibration target just wasn't detected anymore. Yeah, so this is how this looks like. We do see that there's minor errors in tracking, but at least in my opinion, the majority still works fine. So lighting for this system might not be a huge issue. If you have difficult conditions, still might work fine. Might be worth a small test. Then we have minor scene occlusions. You might have to put something in the scene like a table. The person might have to manipulate something. So it's important that the system is robust against such occlusions, right? Again, this will work fine. We put a simple table in front of it, 3 cameras, recorded it. Oh, this one's not the. Oh, this one's the one with the table on it. Tracking worked fairly fine with 3 cameras. What we do see is that for the left and the right camera, the person was in full view at the start of the video, right? So at the start, when he's sitting down, the top camera and the bottom camera see him entirely. There's no occlusion. The middle camera, the one from the front, this one's always occluded. We're just gonna keep this. 2 cameras, still works fine. Nothing to report. Interestingly, with 3 cameras with a larger occlusion. So what we would gather is, let's say we have multiple cameras, we want to guarantee that at least a pair of cameras sees the person at all times. Because that should, in theory, give you all of the information you need to do this 3D reconstruction. So what we did here is we simulated a fairly large occlusion on the front-facing camera. And yeah, when you see the reconstruction, it's cool. I mean, yeah, something's going wrong. So this doesn't work. The issue I would say is here is, right, that in this case, if we just had the left and the right camera, as we saw before, we have a video of it, it works fine. So in this particular case, the system has issues even when some of the cameras are occluded and the rest might see the person in full view. So yeah, this is definitely something to keep in mind when you're doing these recordings, right? None of the cameras should have large obstructions. At least that's my suggestion. We do see that, I guess, the top part is tracked fine. It's the legs that just go all over the place. And yeah, I guess to prove it, here's using the same scene, almost identical. It was a different recording, but still the scene is the same and it worked fine. So these are like obstructions that might be put in the scene, but usually or often we can just remove those obstructions, or we can take care not to that the obstructions don't obstruct our recordings. Something that might be a little more difficult is self-occlusions. So to get an idea of the issue that we're dealing with here, some of the parts, person's body might be hidden behind the other parts. I just want to walk one. So here we had a bit slightly different setting. The camera positions were, I guess, less than optimal as well. And what you see is when Leon, our subject, turns around, his left hand gets hidden from the view of both cameras, more or less, somewhere around here. His right arm, right? And unfortunately, using this model, using this software, when the hand isn't visible anymore, it just sort of pulls it back towards its origin. This might be you might think this isn't an issue if I'm not interested in the hands of the person. If I'm not interested in what's dealing with his hands, I'm only interested in his legs and his knees. But if you take a look closer, we'll see that when this pull happens, it's so severe that it also sort of affects the position of its legs and his feet. So I would say this is not an ideal situation, but it's something that's very hard to avoid, right? Because almost always you will have some part, some rotation, some movement that will occlude a part of the body from more or less all of your cameras. It would be good if we could minimize this effect if we could somehow solve it differently. Yeah, so, okay, I went through some of the issues that we tried, some of the issues that we took a look at. And basically, I'd say the only big issue that we found is occlusions, right? If the cameras don't see the person or see a part of the body, the tracking starts missing, the tracking goes off, and it could affect the parts of the body that it does see. So basically, how could we fix this? The biggest problem is camera positioning, right? It's very important how we set up the cameras so they see the person in full view, and also that they have the required information to do the depth reconstruction and position estimation. So classically in computer vision, when you have depth cameras, we usually just put two cameras near each other, parallel, sort of something like this, and we get a stereo camera. We can get depth from this. This is how this looks like. So we have this green area, right? This is the part of the scene that both cameras sees. So the closer we put the cameras, the larger this darker green area is. More of the scene can be used to do the 3D reconstruction. Because the parts, if we have only two cameras, the parts that only one camera sees, we can't really estimate the position in 3D space. So on one hand, this would be useful to get a large use out of, I guess, the area that the cameras cover. But unfortunately, when the cameras are close together, this also reduces the depth accuracy, or rather the ease of depth estimation. So actually what we would want is to put the cameras further apart. Also, this circle here, this is like my representation of a subject, of a person. And this is the shadow that is casting relative to the cameras. So these light gray regions, that's like, so this part can't be seen by this camera, and on the other side, this part can't be seen by the other camera, right? So these are like the shadows that it casts relative to the cameras. And in the middle, we have this large part where none of the cameras sees this subject. And you see when they're close together, when the subject is close, this area behind the subject is rather large, and it can extend further behind the subject. So I guess the issue is, let's say we have a hand behind here. If the cameras don't see it, then the model can predict it anywhere within the volume that the cameras don't see. So if we can minimize that volume, it shouldn't have such a drastic failure in tracking, right? So what the author suggests, put the cameras further apart. It said that this angle between the subject and the cameras, so this angle here should be around 30 degrees. Two issues we have with this, right? Now, the common area is further away from the camera, so we need a much bigger space. And at the same time, the effective area of each image that can be used for 3D reconstruction, because this is basically what happens here, is it gets smaller. Less of the image can be used for the actual movement of the person for the 3D reconstruction. Also, because the person is further away, it's smaller relative to the picture, right? So it takes up less pixels. The accuracy of the detection will also be lower. So I'd say this would work. This would probably really be the best solution if we have the space, if we have high resolution cameras. I would propose a slightly different configuration. I would angle the cameras inside to get a slightly narrower common field of view. We could place the person closer to the cameras and sort of almost reduce the shadow area behind it to limit the space in which the hand can move. So really, the final, like, my final suggestion would be to put the cameras as far apart as possible. If we're in a tight hallway, then we just put them at each wall. If we're outside, then we just set it up whatever works best, right? And angle them towards our person, sort of towards each other. Are there any better positions? Or if we have more cameras, how could we position them to completely remove any occlusions or solve this issue? So this would be my suggestion. Just take 3 cameras and put them on opposite sides of the person. Does anybody quickly see a problem with this setup? Does anybody suggest a better setup? Might have an idea that would work well. So the main issue with this is, like, we could do it this way. The issue is with OpenCap, we can't calibrate these cameras, right? Or we would have difficulties calibrating them because you can't set up a 2-dimensional flat calibration target to be seen by all 3 cameras if they're pointing at each other in different directions. Technically, this is actually a technically solvable problem. We could have multiple calibration targets, or we could have a 3D calibration target that would be able to calibrate all these cameras together. Unfortunately, at the moment, this is not something they have implemented. The big issue with that is that then you have a problem of how to actually produce the calibration target. Right now, you just print it out on a printer. It's fine. If it's 3D, then you're going to have some problems how to accurately reconstruct it, right? Maybe if you have an accurate 3D printer, that might help you. But yeah, so these kinds of systems might be a bit far for the current state of the software. We just did a few tests how this affects. We put 2 cameras very close to see how, if we put them next to each other, point them at the person, what kind of reconstruction we'll get. Some of these might turn out very funny. So this is what was like when the cameras were next to each other. Didn't move very far, had very bad posture. Very weird. Put them closer together. Gradually increase the distance until we found a distance where the calibration worked well. So if this is an issue you do run into, I'd say like the most obvious solution is try to reposition your cameras and place them either further apart or angle them. Oh dear. We also did some. How can I continue from this point on? Okay. So we also did a test with synchronization with a CMG. Usually, or a lot of you, if you take these measurements, you also want to take some other measurements, EMG or maybe something else. Fortunately, synchronization is very simple, right? You might already have an idea. What we have this little box that we put in the scene, and we have an external trigger. We have some trigger source that makes the light go dim. So then basically I can simulate this here. When we give it a pulse trigger, we also measure the pulse trigger with our whatever capture machine we have, like Quattrocento, and we get the pulse in Quattrocento signals, we get the pulse in video. The OpenCap also calibrates the video that it gives us with the measurements that it gives us. So then all we have to do is look at the color value of this little spot. In my experiments, I put it a bit too far, so I had to do it manually. But if you put it close enough, this is very easy to also detect automatically. You get this value of the red channel of these pixels, right? When the light goes dim, the value goes down, you find a threshold, and you get your synchronization pulse, or rather trigger. You can compare that. Here we have a signal OpenCap and its trigger, and then our SEMG signal with the trigger that we recorded there. I took all of the down steps from the trigger, took the first one, said this is the start of my signal, took the second one, this is the end, and just interpolated them, or rather synchronized them by displaying them in a graph. So now my SEMG is aligned with whatever my kinematics recordings showed. Some technical limitations which we already discussed, so maybe skip these. Go back to your part if you want to add anything.
Yeah, sure. So thank you, Martin, for your really in-depth explanation of technical. Yeah. So I would just few examples when we use this this tool. So we again had a study. We've basically taken a lot of taking a lot of measurements from female athletes. Usually, again, mainly functional tests. So there were, I apologize for this in Slovene, but it's counter movement jumps, squat jumps, Nordic hamstring measurements, some muscle contractile properties measurements, and so on. And since there are just functional movements, the idea is to take these measurements and with some machine learning algorithms try to understand how these athletes can get injured. So it's some sort of prediction models. But we also integrated this with some more, let's say, with some particular tests. One of those tests is the so-called drop jumps. So you can do it with both legs, or you can do it with unilaterally, so jumping on only one leg. And there is this valgus, knee valgus movements usually that is reflecting lower activity, usually in the quads or in the abductors of the hips. So measuring this can be done or via, of course, a marker system. So again, we said before, it's really difficult to do it in a on the field, and on the other hand, with a two-dimensional front-facing camera. And again, this is usually a lot of manual work, and again, we cannot distinguish the rotations and the translations of the knee. So this is the work of NA, which is our master student. So we tried with this OpenCap. We bought the equipment, which is not that expensive, compared at least with other, of course, equipment, and we get something like that. So unilateral drop jumps. Oh, this is not unilateral, okay. Single leg, okay. Yeah. So the idea is to land with one leg, so we can focus only on this valgus knee position, or also on the position of the trunk, because we know that in female athletes, for example, the trunk is a lot more erected compared to male athletes, and might cause injuries.
Control Shift Tab.
And yeah, this was an example that we usefully, or we were still doing data collection, but we usefully use this tool. And there is fortunately a case or a study which we tried to use it, but we didn't be able to use it. So Luca, also my collaborator, he is having a study on stroke patients, really early stage of stroke. I think that he's measuring after 3 or 4 days after the stroke happens. So he wanted to see how the gait get better after in the first basically 21 days after the stroke. And we tried to use this technology, but you will see that the setting was really the environment basically where we measured was really not that good. So we measured it in a really narrow corridor with a really strong light from the behind. So as before Martin said, that it might not be the problem, but combining all these let's say small issues together, then you get really bad results. In fact, you will see that when we try to to compute the model, you see that it's not really a realistic model. So no, Control Shift.
Control.
Okay. Yes,
Depends on where.
and we try to dim the background. We try to dim the background. This time we actually get the model working a little better, but still there are a lot of glitching and movement that are not natural. And also we figured it out that the task was 5 meter walking, and being in a so narrow corridor, it was basically impossible to get the whole model in our recording. So unfortunately, we had to stop it and not work and not use this technology. So sometimes you get what you get, and the possibilities in the hospital setting was really restrictive. They didn't allow us to use a physiotherapy room that is a lot bigger, and unfortunately, we didn't use the technology. So I think that's a promising technology. It's relatively cheap compared to other really high-end systems. Of course, has its limitations. There is limited to 60 hertz per, so 60 hertz, or I think that there is a way to get it on 120, but still I think that is still a in development or not that stable. And something that Martin maybe didn't talk about in his technical part is that this model is relatively simple compared to basically the models that you can get in OpenSim. So the degrees of freedom of the joints are really only the simplest ones. So for example, in the knee angle, you cannot get the rotational moments or the translational moments between the tibia and the femur. So we know that this is a limitation, especially when we do single leg landings, and the results are of course confounded by this. But still, I think it's better than using two-dimensional video recording. So simple single camera recordings, and yeah, that's how my conclusion. I don't know if you want to add something.
Not really. Thank you for your attention.
And
Oh
yeah, we can show the.
We never looked at our results, right? But we'll keep it here. This one's finished. We'll keep it here, or if there is not enough room, we'll set it up later. If anybody wants to try it, you can test it. You can either just make recordings, or I guess we could also try to make every step of the way. You can just try how it works. This is our result before. I think it's pretty good. Right?
Yeah.
Thank you.